Hey, what's going on, guys? Hope everyone's doing really well. As usual, it's going to be a pretty technical video this week. Whenever I look at the analytics, the technical videos always do a little worse than some of the more live and like mushy videos, which those are also good too, but I know there are a handful of people on the channel that still appreciate some of the more hardcore kind of tech videos. So this week's video is going to be hardware related, and it's going to be an introduction to ARM. All right, so there's definitely a learning, kind of a basic level of requirements before this will make any sense. I would suggest at least to watch my computer systems playlist. So basic knowledge of RAM, memory hierarchy, processors, all that stuff. Please go watch that stuff first if you haven't, or else this video won't make too much sense. All right, so what we're going to talk about here is on the left, I have this crazy 2,000-page ARM architecture reference manual for a specific ARM specification. All right, and what we're going to do is I'm going to keep this open on the left. We're going to walk through it together, and I have some notes on the right to explain some of the stuff on the left. So let's just get to it. So if you guys remember ARM is just a very, very popular processor specification, usually found in like a lot of chips in mobile phones, a lot of embedded devices. There's definitely a lot of processor these days that are implementing ARM instruction sets. All right, it was originally a British company, I think, that made this specification, and it's a little old, and it's definitely grown over a long period of time. And this is even an outdated document that I somehow was able to get my hands on, but it's ARM v7a. And this is not the latest architecture. I think they're out with V8 or V9 or something, but this is going to be a walkthrough of the ARM v7a architecture, and we're just going to walk through this document. All right, so 2,000 pages, but it's not so bad. I'll read some important stuff if we go across it. This stuff, table of contents, let's just go straight to the intro. So about the ARM architecture, let's just read what they wrote. So maybe they do a better job of explaining it. The ARM architecture supports implementations across a wide range of performance points. It is established as the dominant architecture in many market segments. The architectural simplicity of ARM processors leads to very small implementations, blah, blah, blah. Okay, so pretty much what they're saying here is that we're awesome, this is a great architecture, and you should implement processors for our architecture, right? Remember, guys, always distinguish the architecture or the specification versus the implementation. So like Pentium 1, 2, 3, 4, they're all different implementations of one specification, right? So in the document on the left, we're going through the specification of V7, but there's so many implementations by different companies around the world for this architecture, all right? And we're just going to walk through the specifications. So first thing to know is that the ARM architecture is a reduced instruction set computer, or a RISC architecture. So what does RISC really mean? But let's just go over to the left a little bit. So there's always been this old debate. I don't even know if this is really a debate anymore, but like this was like a popular interview question when I was in school. But it's pretty much the differences between a RISC and a CISC instruction set computer. All right, so the key word to understand, the key differentiating word is reduced versus complex. All right, so ARM architecture is the reduced kind. So what are some differences between complex and reduced computers? So right off the bat, complex computer has a large number of complex instructions, and a RISC computer has fewer, more simple instructions. All right, so very few instructions, but you can probably build up simple instructions to make complex instructions. The next major difference is that CISC computers have variable length encodings, and this is good for code density, and I'll explain this a little more, whereas RISC has fixed length encodings for all its instructions. So let's just take an example, but let's say there's a computer instruction like add R0 to R1. Like this is an assembly instruction, right, guys? What a fixed length encoding means is that this is always a set number of digits, whatever length this might be, and this is always the same for any single instruction, whether that's add, jump, any instruction will have the same exact length of encoding. So when they say variable encoding, that kind of means that the length of these encodings can differ. So add might be like, maybe add is just a few, but then you have like a multiply, and that's like a lot, much more complicated, and it's a different length. Then you have like divide, and that's like a little shorter. But one of the really key characteristics of RISC was that you could have variable length encodings for all these different instructions, and it was actually very good for code density because some instructions are really simple. You don't really need a lot of binary to represent it. All right, and for RISC, all these are the same. All right, so that's kind of what this means by fixed length encodings. Every instruction is 4 bytes, and variable length encodings. So last major difference, there are a lot of other differences between these two architectures, and I would encourage everyone to go ahead and read about them. But one thing that you can do in a RISC, damn that word, the RISC system, is that math operations you can do directly on memory or registers, which is pretty crazy too. So you could have like one specific instruction that can manipulate like something in memory. And that sounds intuitive, right? But just compare that with how RISC works. So in a RISC system, all the operations are only allowed on registers. So if you want to access something in memory, it's actually a two-step process. You have to access the memory. You have to first load the memory into the registers before you work with them. All right, so it's actually quite different. Everything you do in a RISC system has to be done on registers. If you need to use something from memory, you need to get that thing from memory and load it up. So this is also, if these words don't make sense, I have one video on the memory hierarchy, which you should watch, which kind of spells out all the different levels of memory. And remember, registers are the closest level of memory to the processor. All right. So let's just keep going on the left here. This video is going to be pretty long. I'll probably split it up into 2 parts, but that's just the basic introduction of the ARM architecture. All right. Another thing they have that's kind of cool is they have 2 different instruction sets. So they have an ARM instruction set, and they have this thing called a thumb instruction set, which is kind of like shorter instructions. So let's just read the thing on the left first. So the ARM instruction set is a set of 32-bit instructions providing comprehensive data processing, whatever. The thumb instruction set was developed as a 16-bit instruction set with a subset of functionality of the ARM set. It provides significantly improved code density at a cost of some reduction in performance. A processor executing thumb instructions can change to execute ARM instructions for performance critical segments, in particular for handling interrupts. All right, so I guess the main thing that, if we look on the left a little bit, is that these are just actually 2 different instruction sets that one specification has defined. All right, and they have different use cases, so this is pretty cool. But thumb is kind of, you can think of the thumb as like a subset of ARM functionality. The instructions are also much smaller, like they mentioned on the left. Thumb has 16-bit size instructions, which are 2 bytes, whereas remember, ARM has 32-bit instructions, which are 4 bytes. So each instruction is half the size, so like your code level will be much smaller. Another important thing to note is that these instructions are very different, right? An ARM instruction is 32 bits, and a thumb instruction is 16 bits. So a processor can either process thumb instructions or ARM instructions, but not at the same time, right? So a processor is kind of going in thumb mode because you can't like interlace these instructions and expect the processor to understand. If we're in thumb mode, we're expecting thumb instructions. If we're in ARM mode, we're expecting ARM instructions. So those are kind of different modes of operation for the processor, And as they said in this paragraph is that, there might be special use cases where you would want to use like thumb over ARM or something. All right. So that's actually another really cool feature of ARM, is because they have two different instruction sets embedded in the same specification. So let's keep it moving. Oh, this part is pretty cool. So this is where the word A comes from. So architecture, version, profiles, and variants. So these things are always evolving. So the ARM and thumb instruction set architectures have evolved significantly over time. And the ARM version 7 has a different profile, right? It actually says it has 3 different profiles, and each of them is really different. So let's just read about each one real quick. There's an A, there's an R, and there's an M. So the A is an application profile. So this implements a traditional ARM architecture with multiple modes. But application profile, this is confusing. But what application profile means is that this is like the beefiest one, like the strongest one. This is meant to be used for like application processors running like really big operating systems, running really big applications. All right. The R is for real-time profile. So real-time is a little different, right? If you have a real-time system, that's kind of like a missile on the ship, or something that actually is broken if it doesn't execute in a certain amount of time. That's what real-time means, right? If our computers are slow, then that sucks. If like a radar is slow or something super real-time, that's actually, it's broken. So that's the real difference in that system. Real-time systems really need to finish stuff at a certain time, or else they're just straight up broken. The last profile is this microcontroller profile. So this is probably the most simplistic one, designed for microcontrollers. Microcontrollers are very simple. Think of microcontrollers as like the thing in your like your fridge or your microwave, or maybe the car dashboard, or like really simple, or like the toaster. Like your toaster probably has a microcontroller in it. So these are very like small, simple, like kind of small, simple hardware, and ARM has a profile for that. So it's kind of like 3 different profiles depending on what you need. So if you're building a rocket, maybe you need to use this real-time profile. If you're building like a mobile phone, maybe you need the application one. If you're building a toaster, maybe you need the microcontroller one. All right. And here is, oh, this is actually pretty cool. So this document I picked is just ARM version 7, but it's gone through a lot of different versions and evolutions. So I just picked 7. 8 is already out, but they give you a little historical view of how it's evolved over time. Like ARM version 4, this is the earliest architecture variant. It includes only the ARM instruction sets. Version 4T, they added thumb. Version 5T, they improved interworking of ARM and thumb instructions. They added a couple important instructions. ARM 5TE, they added more instructions. So this is like the evolution up to 7, and it'll continue to evolve, right? So that's pretty cool. So this section just talks about all these different versions. Wow, there's a lot. So obviously some of them are obsolete, but yeah, just keep going. All right, ARM, actually we're coming up on, I'm going to finish this off as part 1. Actually, this video is so technical that I need to break it up into parts properly, because I do want to discuss every section and make sure I talk about each section pretty well and not skip over it. So I'm going to make another part of this video, and we're going to dive straight into this extension part in part 2. All right, guys. So go on to the next one.